Plastic evaluation is our core expertise at Gradical. We help medical technology companies choose the right plastic for their application with the technical suitability, regulatory compliance, and improved sustainability. Learn more under www.gradical.ch/plastic-evaluation. Our guest today is Julian Lotz. Julian is co-founder and CEO of BIOVOX, a German startup focused on making medical-grade plastics more sustainable. He's an expert for sustainable medical grades and especially for bio-based grades. Here's our discussion. Hi, Julian, and welcome to the English version of the Gradical podcast.
Hi, Lucas.
What is a bioplastic and how are they produced?
Well, bioplastics, there's two different dimensions that you usually can find in literature. First one, and that is the one that is most important for us at BioVox, is a polymer that is actually made from biomass. So you're putting some feedstocks into the production of the polymers that are derived from plants usually. There could also be derived from animals, like chitosan, for example, but technically relevant in our field, that's plant-based materials. The other dimension is the dimension of biodegradability, and that doesn't necessarily mean that the material is made out of plants. That could also be a fossil material that's degradable, like peanut in those films that you have in agricultural applications. So this is the other dimension, but that is, from my perspective, much less relevant in the field of healthcare.
Okay, so you have either biodegradability and you have the bio-based version. So, and how are they produced? If we're talking about bio-based, how would you produce such a plastic?
Most of the current biopolymers are produced through fermentation processes. So it's a biotechnological process. You usually take energy plants that will bring you sugars or starches or fats, usually oils, and then especially with the sugar and starch-based materials, then you're fermenting that towards ethanol or lactic acid, for example, and then you go forward towards the polymers like polylactic acid, biopolyethylene, or with sorbitol, for example, to polycarbonate-like materials. So there's a lot of variety in there. Or the other one, where you don't produce a monomer, but actually produce directly a polymer, that would be the PHAs, polyhydroxyalkanoates, where you use some sort of the fat of the bacteria. So if they get fat and are fed a lot and get bigger and bigger, they tend to store the energy into the polymer itself, and you can use those energy reserves of the bacteria directly as a polymer.
Okay. And then you would have to extract that too.
Exactly. And that is also one difficulty that I see for the healthcare applications. We are currently having a look into those materials also. They're quite interesting because you could use green hydrogen and captured carbon to feed the bacteria. So you wouldn't even need plants for that, just exhaust from cement plants or something like that. But then you have quite often residues of the bacteria hulls, and that could be, of course, endotoxic or pyrogenic, and there's the purity is very important for those materials if it comes to blood contact, for example.
Yeah, that's then biological substances, and then you would have to incorporate that knowledge into your biocompatibility risk assessment.
Exactly, or in the production processes so that you get enough purity in there. If you are looking at those biopolymers that are produced from monomers produced through fermentation, like PLA or PE, for example, that is not a risk because there you don't have any residues of the bacteria or yeasts in there.
Okay. And if you're looking at what's available on the market, you talked about what is technically possible, but what is like the let's say leading bio-based polymer types on the market? What is offered on the market, and what do you offer as BioVox?
Yeah. So the producers of biopolymers usually come from applications that address mass markets like food packaging, for example, or let's say that not all too high-techy applications, consumer products, packaging, etc. So we find mostly in terms of mass PLA and biopolyethylene. Those are, I think, the largest groups that are actually bio-based to almost the full contained of carbon. Then there's the mass balance approach bioplastics. There you find a bit more variety, of course. There, a part of the plastic usually is made from plants. There's a mixed feedstock between fossil materials and bio-based materials, or sometimes it's different feedstock streams and they are separated, but certificates are exchanged. So a little bit as with electricity, there you also can find styrenics or polypropylene, for example. And then there's some specialities that are a little bit more technical, like polycarbonate, like partially bio-based materials. But most of the materials are, let's say, that the equivalents of mass plastics or part of the technical plastics.
Okay. So what you usually find is that you have the commodities and the technical engineering plastics sometimes, but even there, it's like the lower tiers of engineering plastics. So I would say
quite often.
I would say like
and the bio PAs, of course, forgot to mention them. Bio-based PA is quite a classic also. So there you are fully inside of the technical realm of plastics, of course.
Yeah. There's for polyamide 11 and 10. Yep. There's a very common route of bio-based feedstock that you find there, but it's actually easier than doing it from fossil. So therefore, this was developed a long time ago, not having sustainability in mind, but it's just like the more cost-effective way of doing it, because the amino acid is produced by a actual oil that has a convenient double bond at the exact right distance from the carboxylic acid, and therefore it's just the easiest way to do it. But what you also see is that if you want to have a sustainability advantage in the CO2 footprint advantage, you have let's say the carbon that you take into the polymer from the atmosphere. So a plant or a bacteria or something like that uses CO2 from the atmosphere to build its molecules. And therefore you absorb carbon from the atmosphere, and therefore you get let's say a credit for your LCA. And this credit is usually between 2 and 3 kilograms of CO2 per kilogram of plastic. And this is basically fixed across all types of plastic. So for a commodity, this is great news, because this is basically all my CO2 footprint that I have. So usually you can also find LCAs that state, we are negative. So we're negative half a kilo or something like that. A CO2 footprint, because we take up 2.5 kilos and our polymer usually has 2, and therefore the difference is minus 0.5, which is cradle to gate, of course, not taking into account the end of life. However, this is like a great percentage. But if you go up the polymer pyramid, and if you go to high performance polymers, you have PEEK that has 20 kilos of CO2 per kilogram of plastic. This is just 10% of the impact. Then you just save 10% by making it bio-based, and with polyethylene, polypropylene, you reduce it 100%, so to say. So the ratio that you can save goes down as you go up the polymer matrix, and therefore you also only find the bio-based in the lower tiers, because there's the advantage. So that's how I see it.
Of course, the advantage of the credits gets lower and lower the higher up you go in terms of the energy amount that has to go into production. Totally correct. But sometimes you can also find quite elegant ways to produce a monomer by a fermentation process, and then you also have a lot less carbon footprint in those currently highly energy intensive processes for fossil-based carbons. Of course, the markets are a lot smaller. That's why there is less research as for the commodity plastics, and that's also why they didn't start there. But if you find some elegant ways to produce more complex monomers or precursors through very energy efficient fermentation processes, then I could imagine, not being a chemist, of course, but I could imagine that there's also a lot of room for carbon reduction for the high performance plastics. But I also see that like more as a research topic or a future topic than relevant for just right now. I mean, of course, the impact
Have you
is
seen
much
an example of that?
not in the high performance plastics, but for example, if you look at PEF, which is more or less a fully bio-based derivative of PET using a furanate instead of a terephthalate, there you have even better properties when it comes to barrier properties, which is quite important, of course, for the applications relevant. And the production of those monomers, FDCA, for example, can be more energy efficient than the production of PET. There is also a lot of research currently ongoing in there, but that's also an example where you maybe could find similar polymers that are more energy efficient in production, not only through incorporation of bio-based carbon, but also through quite efficient processes. Or on the other hand, if you're looking at bio-PE or PLA, there the fermentation processes and the polymerization processes also are quite efficient, and you are often a bit better than you would be for similar plastics on a purely fossil base. Okay. Not by orders of magnitude, of course, but it is absolutely competitive or even better.
Yeah. So you try to find similar chemistries that work with fermentation processes, or that you can produce in a more efficient way. It's not always easy to like replace, or coming from the other way, it's actually usually easier to replace fossil-based polymers with bio-based polymers if there's just a drop-in solution, so chemically equivalent. So I have been using polyethylene for forever, and then now I'm using bio-based polyethylene, and properties are the same, machines are the same, processes are the same. I really like that because I do not have to change too much the work, the way my product and my processes are working. On the other hand, there can be also an advantage of using new plastics with potentially also better properties that have, so to say, a sustainability advantage. And this is certainly an interesting topic. So how close are we to getting PET replaced on a mass scale?
Yeah, PET might still take some 4 to 5 years. From what I would guess. The manufacturers are a bit more optimistic. I'd say 4 to 5 years might be realistic. But it also depends on the product that you're actually trying to replace. If you're looking at pharma packaging with high barrier properties, then you basically would have to wait for PEF if you want to have a monomaterial solution. If we are looking at sterile barrier hard blister packaging, for example, for medical devices, then PLA can also be a great replacement. Has slightly lower temperature stability. So if you are actually needing 60 degrees, that might be a bit close. But if you are, let's say, in moderate conditions, up to 52, 53 degrees Celsius in transport tests, transparency is great. Mechanical properties are the same. Production is pretty much exactly the same, but with lower energy needed for thermoforming. Results are great. So there's also already the option to switch away from PET.
Mm-hmm. So what I've heard with PLA is one of the plastics that is as well bio-based as well as biodegradable. And the biodegradability part is usually something that, like in marketing, if you see it for consumer products, it's usually marketed as something that is very great. And yeah, but biodegradable, and you can throw it into your garden and it will go away. And then if you talk to the development departments in medical device or anything like that, they're like, yeah, degradability is actually an issue. We do not want the polymers to degrade because that reduces our shelf life, and shelf life is something that we have to test for. And what would you say, would you say to that? Is it? I mean, we have the advantage, or you have the advantage, that PLA doesn't degrade too fast.
Yep. You have to have a look on the degradation rates. For example, if you look at biopolymers like PBS or PHAs, depending on stabilization, they significantly change over time. Also in, let's say, standard storing conditions. And there, the material getting brittle, losing strength is an issue. That's why we don't really use them so far. But PLA, there you usually need higher temperatures and or high humidity levels So if you stay at 80% or lower relative humidity, if you stay below like 50 degrees Celsius for long-term conditions, then you don't see much of degradation in the usual 3 or 5 years of shelf life. So that is quite fine, and we have samples here that are in accelerated aging and currently at an equivalent like 7 years or something, and you don't see much of difference to the new material.
Okay.
If you have, for example, a PLA and you want to store watery liquids in there, not that good of an idea. If you want to do it long term for a few days, that's fine. Few weeks, few months, don't do that, basically. Or if you have long time high temperatures, for example, accelerated aging at 60 degrees Celsius, not only does it bend if you are not using fully crystalline versions, but also it gets pretty fast in terms of aging, and it's not comparable anymore to real aging.
Yeah, I mean,
so that's something to take into account.
The thing with accelerated aging is always that people actually don't know what they're doing there. Because accelerated aging is like you bring it up to a certain temperature in the assumption that you are in the same domain of the chemical processes that take place with the same reaction taking place. So there's no other reactions going on there. And what you usually do, or what the recommendation is, to stay below TG. And if you're close to the glass transition temperature, yeah, you basically get other processes involved, and then the
Exactly.
Arrhenius doesn't work anymore. So what you're trying to do is basically do Arrhenius's principle. You assume that the reaction speed is going to increase with time exponentially. And if that doesn't hold, your whole setup doesn't work. And saying that if you're too close to the glass transition temperature, it doesn't work anymore. And with
absolutely.
PLA, that's not the case. You use 55 or 60 degrees for polypropylene. That's pretty suitable for that. However, with PLA, that is not advisable. And then you have to store longer, and they don't like that because you have to store for 3.5 or 4 months instead of 3, and then your development times increases. So, have you experienced in that, or you can just deliver data?
We've done that, and we also found with a customer that did 55 degrees. As you said, the mobility of the polymer chains gets pretty high. Hydrolysis is much more faster. We had 3 months at 55 or 58. I don't exactly remember what they used, but it was like if you would have aged it for 100 years or something like that. So completely not representative anymore. As said, we recommend 50 degrees maximum for PLA. You have slightly increased storage times, of course, for accelerated aging, but then you get quite secure characteristics out of your measurements in the end.
Okay. So,
and we also have some data, so of course documentation contains that.
It's advisable to talk to your material manufacturer in order to make the accelerated aging as accurate or as suitable for your polymer as possible. So question your standards that you have for fossil-based or virgin-based plastics.
And that comes to a lot of processes. What we quite often see, and as you mentioned before, taking a drop-in solution is the easy way, and that's why biopolyethylene also is accepted quite well in the pilot projects that we have, and the people really like it because it's the same basically, low effort. But on the other hand, if you are developing a new product or if you have a major rework of your product, then you can have at a pretty much the same price point. You can have a material with much more stiffness and strength. If you can use these properties to reduce material, for example, to reduce volumes, you can get down the cycle times in injection molding. You have less storage and logistics costs with lower weight and lower volume of the product. There's a lot of additional benefits that you can gain from using high strength, high stiffness materials. And then it's advisable to think a little wider, to do a little bit more of innovation in the product possibly, but then also try to work with the material manufacturer, for example with us, about optimum production parameters, about the testing like the accelerated aging, so that you can ensure that you actually use all the potentials in the material and don't fall into traps that are where material might slightly behave differently compared to a polypropylene, for example.
Yeah, I mean, it's an optimization problem because you have a certain property per environmental impact. Is the same what you would do with cost. So you can compare steel to aluminium to polymer basically, and then you have the property per cost or property per environmental impact that you really want to optimize for. And if you used let's say overkill for before, so you have I've been seeing products where there's a pump in it and there's like just a 3-4 centimeter steel plate in there just because it doesn't have to hold that weight. It's just it was developed that way, and we will always do it like this. You could use like 4 millimeter steel and would be fine. So if you have overkills, it's actually much more. It's much easier to get environmental impact out of your product. If you have a very optimized product, you have a difficult time even getting even better. And therefore, I mean, that's also an issue for like the commodities, because polypropylene, polyethylene actually do not have that much of an environmental impact. Of course, they have their impact, but it's like from the plastics, they're actually the good ones, because it's also actually cheap to make. It's cheap to make them. It's very efficient to make them, and we have been spending decades in making the process more efficient. So therefore, like, it's a challenge to get a lot out of these plastics, or to reduce much from these plastics. If you are using like the high performance plastics, it's actually a lot easier to get the CO2 footprint down just by downgrading something like if you have a peak and then you just go down to a PA6 with glass fiber. And if your developer at the time was just like, yeah, peak will work, it's going to be fine, works fine from the mechanical perspective, and then but you could actually do it with a much cheaper, much environmentally friendlier polymer. That's what I see. Credical is the plastic expert in medical technology and supports you in the areas of sustainable plastics and material compliance. Our course, Sustainable Plastics and Medical Technology, will bring your development team up to date with the latest developments in sustainable plastics. In addition, we offer the course Regulatory Aspects of Plastic Selection at the CATS and the SCATZ, which provides guidance through the maze of regulations when selecting materials. More under www.credical.ch.
Two thoughts on that. Of course, if you have a high carbon footprint in the beginning, then you can reduce greatly. We had a customer with a tube made from PTFE, and with some very elegant design work that they did on their device, we were able to switch towards a polymer blend of biopolyethylenes that we developed for them with a bit specific requirements or characteristics. And they fell down from like almost 30 kilograms of carbon emissions per kilo of tube to around cradle to gate minus 1 or something like that. So that's pretty nice. On the other hand, if you look at other impactors, so of course, if you have polyethylene, for example, and substituted through a biopolyethylene, you are saving, in terms of percentage-wise, you're saving greatly quite often, but in the absolute numbers, it's not extremely high. Mm-hmm. But you have implications with changing towards a more circular material. If you are looking at a fossil virgin material, then this is not taxonomy conform regarding the EU legislation for ESG measurements and assessments. And if you want to be within the EU taxonomy, then you should use recycled material or bio-based materials that fulfill the criteria of being sustainable. So approaches like that. And that will not maybe save you a lot in terms of direct emissions for all of your company, but also doubt on that bit. But that will also reduce your costs, for example, for refinancing, because you get cheaper credits for taxonomy conform business. And then you sometimes get some benefits in areas where you wouldn't expect them to be. If you have a simple product just made of plastic, then the plastic still is your main driver of sustainability, of conformity to the EU taxonomy, and also for the total footprint. And on the other hand, large consumable manufacturer, they have a carbon footprint based on their plastics of around 600,000 tons per year, one of the large ones. And that is just the carbon footprint that they can change and impact over the choice of polymers and just the raw material, plastic as a raw material. And on the other hand, their aggregated scope 1 and scope 2 emissions are also 600,000 tons. So they can buy electric cars and solar panels as much as they want. It's just the same compared to reducing the carbon footprint of their plastics to close to zero. So there is a significant part, even if the majority of those materials are polypropylene and polyethylene already.
Yeah, I mean, usually if you use a lot of plastics and you're a manufacturer of plastic parts, there are two drivers of your CO2 emissions. It's like the plastic you use and the energy you use for your machines, and then like everything else is basically peanuts by that point. It's like the energy usage for like a machine park, if you have a lot of injection molding and extrusion machines, that's significant, and they use green electricity. That's basically the best you can do, and install efficient machinery. And then there's the plastic you use. So that's of course a thing. But what you often hear is like plastics made from, let's say, food or agricultural goods, but they're also not so good for the environment. What would you say to that? If you look more broadly, we're always talking about CO2 and everybody's talking about CO2, but other environmental impact factors are also not to be neglected. What would you say to that?
Absolutely. So the two major problems that I see that are most urgent, we have a lot of environmental problems, definitely, basically in all aspects of environment, the 6 categories of environmental impact. But from our perspective, the most urgent are the global warming and the biodiversity. The other ones are relevant, but can be changed on a bit another timescale and with other measures. So reducing the carbon footprint is the single item that's been talked about most, and it's also very relevant. And there we are very good. What you don't have with fossil plastics, for example, is doing the agricultural processes. You are not fertilizing, you are not using pesticides or anything. So that is actually good with fossil fuels or fossil oils as raw materials. But the impact, it depends always on what's most important for you, your eco assessment, and what do you want to achieve as a company. If you say, we definitely do not want any eutrophication potential to be increased, then you should stay to fossil fuels. But is that the most urgent thing to reduce or to optimize? That's the question that you have to ask yourself. And then there's the thing of the technology S-curves. So far, we are a lot better usually in carbon footprints with many bioplastics or most bioplastics. You get worse, as said, for example, with eutrophication potential or basically everything that has to do with the soil
water, land usage.
Water. Yeah, and there is potential to reduce that. For example, land use. 14.7% of the farmland that is already used today could sustain all of the plastics production of today 14. If we just use sugars and starches. 14.7, I think, was the last number from the IFBB report.
Okay.
If you calculate it down to farmland, actual farmland, not agricultural land, but really farmland. And if we take into account that we are currently not that good in terms of circular economy and recycling, there's a lot of potential worldwide. We maybe could come down to like 4 to 5% of the current farmland. And that's not that much, considering that you have 5 to 7% for energy crops to make biofuels. That might go down with electrification. That we have food waste of 25 to 33%, depending on the statistics that you're quoting. 70%, around 70% of the food that's produced, or the agricultural goods, are for feeding animals. So consuming a little less milk and meat doesn't need to be zero, but a little less would also give us the 5% of land. So that is quite easy. And then there's the thing how we do produce those goods. Today, agricultural processes are not that eco-friendly quite often. Extensive use of fertilizers, etc. There's already statistics, for example, I think Boston Consulting did that, or McKinsey, one of both, for the German, the Deutscher Bauernverband, so the Farmers Association in Germany. And they found actually out that after a few years of using less fertilizers and less crop protection, the soil quality would increase by such a high margin that the yields would be pretty much the same as today again. So there are options to produce the feedstocks much more sustainable than we do today, but that's more like a political topic. And if we look at this as an S-curve, polypropylene, polyethylene, for example, or also styrenics, all of the materials that we are using today, they are optimized, as you said, over decades. They are extremely efficient in all their processes. And how we do farming, how we produce newer sorts of polymers is not that optimized. So there is a lot of potential to get better and better in those categories where bioplastics currently might be not as good as a fossil material. And as said, in the urgent categories, saving the climate, for example, there we are much better already. And from our perspective, it's about starting, doing the urgent things better already, and then keep on pushing to reduce the impact of the other categories. Mm-hmm. Like, for example, using PHAs that are made from captured carbon and green hydrogen, for example.
Okay, cool. Thank you for the insights. So that was talking on environmental impact, but like you do bio-based medical grades as a company. And what do you see are the biggest advantages and challenges in implementing this? So of course, using bio-based plastics, the big advantage is that it's more sustainable. And that's your one card that you have as an advantage. What are the challenges in implementing this? Do you enjoy the podcast? Then subscribe and rate it on your platform. And join the discussion on LinkedIn. Your feedback and comments help us improve the podcast and bring relevant topics to you. Let's form a better world with plastics.
I'd not only say it's the one card, there's also, I call it always the future proofness. You usually find less critical substances in biopolymers. So the monomers are usually not critical. And also regarding additives, we are quite on the lower end of using additives at all, as usual in medical, but also then additives that are not toxic in any way. So regarding patient safety, you can also be better. And some of the materials like the PLA are resorbable in general by the human body. So if you have some particles that come off of a medical device and that get incorporated in a surgery, for example, that might be not as persistent as, for example, a polypropylene part. So there's some other advantages too. Difficulties, as you mentioned before, if it's not a drop-in, it's of course more efforts to develop a new material or to develop a new product with a new material, to do the testing. Somebody has to want such a solution a bit more than the current materials. So I'd say the risk averseness of doing anything new is one of the biggest challenges. of using bioplastics in the medical sector.
Yeah, I would
Safety wise, that's all fine.
I would say that's the general issue in the medical sector. It's like we do what we always did because we know changing anything is such a pain that we do not
Yep.
want to do it, and we're currently
Yep.
still occupied by getting MDR right. So,
but from my perspective, that gets better by the day. So many companies are almost through or pretty much through. So I hope that is over in 2025 somewhere.
yeah, we hope so. Yeah, so let's get to more of the personal stuff. You are a startup founder in Germany. How was that, and how was it to assemble the team, to get the product right, to find your first customers? Tell us about your journey.
The journey was not that straightforward. We were coming from implantable and resorbable materials, and their biodegradability is important as one of the exceptions. But we wanted to use different biopolymers than we use today, and in 3D printing processes that turned out to be really basic research. So maybe not that good for a startup developing implants for a relatively niche market and with a highly complex technology. So we changed that towards the application of plastics as a technical material in medical devices, pharma packaging, etc. That took some 2 years. But then we found that the product market fit was also quite good because back then the first companies, not that many, but the first ones, they really were searching for more sustainable alternatives because they had internal targets to reduce fossil-based materials, to get more circularity into their raw materials. And starting the first projects was actually quite easy. What is not as easy, and that connects to what I said before, is actually getting products into serial production, because then in the end, many customers, they are searching for sustainable solutions because they know they have to have them at some point. But that point is not past already. So they say, hey, I now found something and that works quite nicely. So I'll have that in my drawer and pull it out when legislation changes and I have to do it. But to survive as a startup until somebody really needs to do it and not just wants to do it at some point, that might be a bit challenging. And that's also the difficulty, finding financing for this not too short period of time that you need in order to have enough revenue in medical sector if you are a newcomer.
Yeah, and then of course your customers also have to test and approve the product, so they have to do biocompatibility. I doubt that they have any data on their device made from a bio-based plastic like yours, so they also have to potentially argue that they're clinically equivalent. So good luck with making clinical trials. I mean,
depending on the product, yeah. That's
and then I mean,
some
also
work,
commenting on your first plan, like highly complex technically, and implementation and approval times of 10 years, something like that. So an implantable device, you'll have to go through clinical trials, and that costs a metric ton of money. And on top of that, it's going to take a lot of time. So probably a good pivot, life-saving one.
Yeah, I mean, we are, in the end, we are engineers here. So we also have a chemist in the team, of course, and some plastic technology experts. But in the end, we are all more or less engineers and searching the best and right materials for future devices and packaging. That is also closer to our core competencies than the therapeutical aspects of osteosynthesis. So,
okay. So tell us about the vision that you have for your company.
yeah, our vision is to actually bring circularity into the healthcare system, saving the economy and ecology of healthcare. In our perception, just goes hand in hand with circular economy. We can't afford to discard virgin materials that are high quality and also often high cost and just incinerate them. There's way too much value in the materials, so we need to recover we need to use materials from renewable resources so that we have them for the next decades to come and not just for the next 1 or 2. And from our perspective, having safety in terms of having the right medical devices all the time available and not damaging the people and the planet, and also be competitive long term, that in our perspective can only work with a circular economy, and their renewable feedstocks are as important as recycling the materials that are already in the technosphere. And that's why we work on renewable raw materials and also on recycling processes for those materials together with partners, so that we can, in the end, actually keep the resources that we have in the healthcare in the loop and reduce costs and also environmental impact greatly.
Should be a breeze, huh?
Should be. But then there's the effort that you mentioned before of implementing new processes and products. And it's not ultra fast, but we think that it's worth fighting for it and working on it. And fortunately, a lot of customers see it like that. So it takes time, but we're optimistic.
Okay.
There's not much of an alternative, actually. So
how did you put together your team to realize that vision?
The founder team, basically, Carmen, I already knew from my time being researcher at the university here. So she was working at our department too. And that was pretty much a no-brainer. And since we got to know him at the local startup and innovation fair, also hosted by the university here. He was at a neighboring research institute, but we never met actually. But he worked on implantable, resorbable bone replacement implants, so almost the same topic. He found us, he said, hey, that's pretty much what I want to do. And so that was the founder team then with the Access grant that we got, 3 persons. When it comes to the employees, that's actually something that I really like. If you are doing something with a lot of purpose, helping people, being in the medical field, but also helping the environment by reducing the impact of helping people. That's something that really motivates a lot of very intelligent and reflected people. And we also, or all the time, we get applications by initiative of really good people with a good background, cool personalities. So that's actually relatively easy, keeping the team growing.
So that's the easy part. Getting a team is the easy part if you do something that is good.
Basically,
and what's the difficult part?
I said having the money for doing that over years and years and years, like in the medical field. There's not too many investors that understand the field and the investment horizons that you need for that, and also convincing the customers that getting started is important, and getting started doesn't stop at having a prototype. That's nice, but also means that you bring something into serial production, because if that doesn't happen, then you don't have the reduction in impact, you don't have the benefits that you get in marketing, and you maybe don't have the supplier anymore in a few years if they don't sell anything. That's also something that I heard from Bernd from Ineos at the Ultra Polymers event, where he also said, hey, we have some styrenics that are mass balanced bio-based. They are more sustainable. You have to buy them, otherwise we can't continue making them. So all of the industry wants more sustainable materials, but in the end doesn't buy as much as it would be needed. So that is the difficult part, getting this hen and egg problem solved.
Yeah, my dad used to say, or he still says it, the only way you're being innovative is when you can send invoices.
Yep.
It's like innovation is when you can send an invoice. It's like an invention. It's like you have something that kind of works, but you haven't commercialized it yet. But you need to commercialize it, and you put the power on the street, basically.
Absolutely.
Okay. So last question. What advice would you give to our listeners in the area of bio-based or sustainable medical grades?
Yeah, basically, first step is always make yourself free of what you've done so far. because as you mentioned with the overspec'd products, think about what you actually want and need in a product regarding the material's characteristics, and where you could be flexible. Because by opening up your requirements a little bit and take them back to what's actually needed, you get a lot larger solution space. There's a lot more different materials that you then possibly can use compared to a very narrow and tightly bound specification. And if you're then going towards like polyolefins coming from more technical materials, or if you're going to bio-based materials, that in the end, everything is a reduction in impact and everything helps. But be open about changes and challenge what you've been doing the last decades. And that really helps you opening up potentials. Also, sometimes for cost savings. So it's not only about impact.
Yeah, I mean, I like those projects the most. The safe environmental impact and safe cost, because you don't have to sell those; they fly on their own.
Yep.
Because you win everywhere. What I would like to add to that is measure what the environmental impact reduction actually means. So you have to do LCAs, because what I see a lot is, I think this is more sustainable, so I'll just use that. So I'll use paper and make it four times as thick, because it doesn't work at that point. And you actually, if you would calculate, you increase the impact, but you just think you're doing good and you're not actually doing good. So
definitely,
way to hell is full of good intentions.
I actually made basically a model of what to do in which order in order to get a sustainable plastics solution. Presented that at a few occasions. So if anybody wants the slides, just reach out to me. Happy to share that.
Okay.
There's also the LCA in there and making a strategy, etc. So step by step.
Perfect. So a few last words from you.
Yeah, it was great to be here again. Always great to talk with open-minded people about medical plastics. Also like the podcast a lot, so thanks for making the podcast, Lucas. It's part of the starting package for everybody that starts at BIOVOX. So everybody gets a few episodes.
Your employees
that are
half my listeners.
Yeah. A few episodes are definitely a must for everyone, and then there's optional episodes depending on the topics that people work on. So it's pretty easy to get into the topic for students, for example, that are starting in the field. That's really cool.
Okay. Which episodes are the obligatory?
Basically the basics about regulatory and testing, quality management. So everything that defines a medical plastic in the end, and then depending on where the people are working in, if it's more the technical issues or recycling or LCA. So that is then the variable part in there.
Very good. So thank you a lot. This was Julian Lotz from BIOVOX, and until the next time.
See you then. Thanks.
Still looking for more in regards to plastics and medical technology? Visit our website www.gradical.ch and inform yourself on the services of Gradical. You can also check out our market report on medical grade plastics on www.medicalgradeplastics.de. Or you attend a training regarding material compliance at CATS or at SKZ. And of course, don't forget to rate and subscribe our podcast wherever you get your podcast. Let's form a better world with plastics.